Alright guys, so let's look at something called indices now. So hi guys, in this video we're going to be covering indices, which you may know as like something to the power of another thing, but it's known as indices because it sometimes contains variables and you need to be able to know like the rules around them rather than just like with simple constants. So for example, we obviously know that if we have something like a cubed equals 27, to find a, we would just cube root everything to get a equals and then cube root of 27, which is equal to 3. But with indices, we have to know some of the laws around it. So for example, if we had like a to the power of x plus 1 times b to the power of, oh no, not a, b to the power, sorry, a to the power of -2 equals 8, we have to know how to like evaluate that kind of thing. So we're going to be looking at some indices laws. So let's get started with the laws first. We'll go into some like easy practice problems to like test our knowledge later. So the first law is that anything to the power of 0 is equal to 1. So for example, so a to the power of 0, where a is not equal to 0, is equal to 1. So for example, if you have like 5 to the power of 0, or 6 to the power of 0, or 7 to the power of 0, or anything like that, or even 8.9265 to the power of 0, that would still, all of those will give you just 1. Well, why might that be? Well, if you think about it, if you're taking, let's take the example of 8 to the power of 0, which we might think is like, it's really weird to be 1, but the reason is because when you're putting something to the power of 8, you're multiplying it by that. You're multiplying, in this case, you're multiplying 8 0 times by itself. And there's only one way of doing that. There's the only thing, if you multiply 8 by 0 times by itself, that will give you 1 because that's the only way of doing it. It won't give you 0. So, by that logic, if you have anything to the power of anything, it cannot give you 0. We can also look at it from a logarithmic point of view. So if you have 8 to the power of 0 equals 1, we can look at it as log 8, 1 equals 0. So in a logarithm, as we know, we can't have 0 over there. So it would make sense that this rule would exist. And that's actually how the logarithmic rule of not allowing like to have this kind of thing, that's where it actually came from. Now rule number 2. A to the power of x times a to the power of y is equal to a to the power of x plus y. So let's say we had 5 to the power of 3 times 5 squared. Well, you might think, oh, well, we can just multiply the indices. That gives us 5 to the power of 6. Well, you can't, because when you're multiplying two indices, they're already raised to the power. You can write it another way. You can write it as, so 5 to the power of 3 is just 5 multiplied by itself 3 times. So 5 times 5 times 5. And then that's multiplied by 5 multiplied by itself twice. So 5 times 5. Which is the same as just removing the brackets and writing 5 to the power of 5. Which is essentially just adding the two indices. So that's the other rule. However, this is not to be confused with rule number 3. Which is a to the power of x raised to the power of y. Which is not a to the power of x plus y, it's a to the power of x, y. So let's say you had 5 squared to the power of 3. This time it would be 5 to the power of 6, because another way of thinking about it is just doing 5 times 5 to the power of 3, which is equal to 5 to the power of 3 times 5 to the power of 3, because we're just raising each thing to the power of 3, which is equal to 5 to the power of 6. Oops, that's a bad 6. Another way of thinking about it is that this is just equal to 25 to the power of 3. When you evaluate it, it's actually the same as 5 to the power of 6. So that's rule number 3. The next rule is quite similar to the other ones. Rule number 4. If you have a to the power of x over a to the power of y, yep, you guessed it, it's a to the power of x minus y. And this is essentially because, let's just test that theory out. Let's say we had 5 to the power of 3 over 5 to the power of 2. Well, that's equal to 5 times 5 times 5 over 5 times 5. And these 5s all cancel out to give 5, which is the same as 5 to the power of 1, which is the same as 5 to the power of 3 minus 2. All right, the next rule we'll be looking at, number 5, is a to the power of b over c is the same as to the root of c times is to the root of the c root of a to the power of b. Because let's take an example. Let's say we had the cube root of 5 squared. That's equal to 5 to the power of 2 over 3. When we look at this, it's actually equal to the cube root of 25, which is smaller than 5 because the square root of 25 is 5. And 5 to the power of something less than 1 will give a number smaller than 5, so that does make sense. Also, in case I forgot to mention, which this is probably pretty obvious, but a to the power of b a to the power of 1 is equal to a. That one's probably the easiest rule. Rule number 7, one that's less commonly known at the beginning of indices. A to the power of negative b is equal to 1 over a to the power of b. It's the reciprocal of it. So let's say you had a over b to the power of negative 2. Well, that's just equal to b squared over a squared because it's the same as b over a squared. And when you square a fraction, you square the numerator and the denominator. So it would give you b squared over a squared. So I think those are basically all the rules that you'll cover in indices. So now let's move on to some minor practice problems with some actual numbers, because that way we can just reinforce our understanding a bit. Okay, so here's our first problem over here. It says 81 over 16 is raised to the power of negative 3 over 4. First thing we want to do is eliminate the negative sign. Way we do that, flip the fraction around and get the reciprocal. That gives us 16 over 81 to the power of 3 over 4. Notice the negative is now gone. Now what we do is we'd actually put it in the form where we can actually evaluate it. So the way we do that is we take the numerator. The numerator obviously represents the power to which this is raised, and the denominator represents the root to which this is put under. So it's to the 4th root because it's a denominator of 4, and it's cubed. 16 over 81 cubed. Now, if we were to do it without a calculator, obviously we could just put this into the calculator and would get a result. Or even we could just put this into the calculator, but this is likely to come up in a non-calculator paper. So we have to do this systematically. Now, it would not be helpful to any of our mental math and to our brains and to our time management to actually cube this and then do this to the 4th root. The way we would do it is actually just put this straight to the 4th root and then cube it, because then we get much smaller numbers to work with. All right, so let's just start off by doing the 4th root of 16. So, well, 2 to the power of 4 is 16, so that means that would be 2. So that's 2. And then the denominator, the 4th root of 81, is actually just 3. So we have 3. And that's cubed. Now, we can easily just cube it. So 2 cubed is 8. And then 3 cubed is 27. So our answer is 8 over 27 for this one. All right, so let's look at the second problem over here. So it says 2a squared times b to the power of negative 2 is divided by 2 to the power of negative 3 times b to the power of negative 4. And we have to write this all in indices. We can't actually evaluate this. So let's break this up. So let's first raise everything to a power. So this one, let's just raise to the power of 1. That would make it much more simple. And let's identify the different rules we need to use. So we have divided sign over here. That means we're going to be subtracting the indices itself and collecting like terms. Then we also have a negative sign in many places. That means we'll need to flip the fraction over in many cases. So let's begin. So we'll start with the collecting like terms. So the 3 pairs of like terms are this. This one doesn't have a pair, but it's on its own. And this. So we're going to be working with those separately. So we can evaluate them separately, actually, because 2 to the power of 1, and then we have the divide sign in between, minus 2 to the power of, let's put 2 to the power of 1 minus in the indices, and then minus 3. because there's a negative here. And that's essentially just 2 to the power of 1 plus 3 because two negatives make a positive, which is 2 to the power of 4. So in the numerator, we'll have 2 to the power of 4. Now we can look at the a squared term. That doesn't change because it's just, there's nothing in the denominator or nothing else to change it. So it's a squared. And then if we're looking b to the power of negative 2 and b to the power of negative 4, well, we can just write it again like we did this part. So b to the power of negative 2 minus, because of the divide sign, minus 4 is equal to b to the power of negative 2 plus 4, which is equal to b squared. So this is added on, and that's our final expression for it. The other way we could do it is, wait, let me just write this out again. 2 to the power of 1 a squared b to the power of negative 2 over 2 to the power of negative 3 b to the power of negative 4. Okay, the other thing we could do is actually just get rid of the negative sign. So we can bring this to this side by getting rid of the negative sign. So what we would do is rewrite this as 2 to the power of 1 because there's no negative sign there, a squared, no negative sign there. And then we take these two and push them there because they both have negative signs. So they'd be multiplied by, let me add a multiply sign to make things easier to read. 2 to the power of 3 because the negative sign is removed, times b to the power of 4 because their negative sign is removed. And then that's divided by, and this one goes down here. Make it b squared because it's got no negative sign. It's got a negative sign in the numerator though. Now we can collect like terms. So these two can be collected. We can add them together because of the laws of indices. So 2 to the power of 4. Then we've got a squared just sitting there. And then this is b to the power of 4 minus b to the power of 4 minus 2, which is b squared. And it gives us the same answer. So those are the two methods of doing this problem. Okay, so let's look at this final problem because this is just an introduction. We'll do some more complicated add math style questions as well in the next video. So 9 times 3 to the power of x minus 1 equals 1 over 27. So obviously we need to solve for x. Now the way we do this, I don't think I mentioned this before, so this is important. We have different bases here, so we can't actually collect them. We can't like add these two exponents together because they're of different bases. But the thing is, it can definitely be made the same base. Notice that 9 can be written as 3 squared. It's a perfect square. That's the same base as this one. Is there a way of writing 27 as the same base? Yes, there is. We can write it as 3 cubed because that's a cube number. So these are some effective ways of doing it. Let me just add on though. Let's say we had 9 to the power of x minus 1. This can be written as 3 squared, but it would be 3 to the power of 2 times x minus 1 because we've changed the base, which makes it 3 to the power of 2x minus 2. Do not make the mistake of just multiplying it by the first term. So don't write it as 3 to the power of 2x minus 1 and forget about this term here. Expand it like a proper brackets question. So that would be the same as that. That's just a side note, but for now we don't need it, thankfully, because we don't have any unknowns in a different base. So first step is always to break it up into the simplest base. So 9 is 3 squared. It's multiplied by 3 to the power of x minus 1, which is equal to 1 over 3 to the power of 3. But it would be much more helpful if we could make this fractionless. So obviously we can use law of indices to make this a negative 1 and bring this to the numerator in that way. So it's 3 squared times 3 to the power of x minus 1, which is equal to 3 to the power of negative 3. Because if we were to evaluate this with exponents, it would be 1 over 3 cubed, which is 1 over 27, which is what we had originally. Let me just erase this, sorry. And write that out again. 1 over 3 cubed, which is equal to 3 to the power of negative 3. Now we can just use the addition rule here because they're the same base. So it's 3 to the power of 2 plus x minus 1, which is equal to 3 to the power of negative 3. That's equal to 3 to the power of x plus 1, which is equal to 3 to the power of negative 3. Now, actually, what we can do, since we have, it's like logarithms. When you have one like base here, we can actually just get rid of it. So it can become x plus 1 is equal to negative 3, because we're just equating the exponents at this point. The bases are the same, that's fine. So that means that x is equal to negative 4, and we can check that with the calculator, but I'm pretty sure this is correct because we've just used this line of working. Anyway, so that's the last question we'll be tackling in this episode. I'll post another video soon of me doing more complicated mathy style questions as well. If you need any help, do let me know in the comments, and thanks so much for watching.